Welcome to this custom-tailored deep dive. Today our mission is to unpack a really fascinating 2026 paper by Lobanov and colleagues. It's from the Fracture and Structural Integrity Journal. And imagine you're looking out your plane window and you see a mechanic just accidentally drop a heavy wrench directly onto the wing.
Yeah, it leaves a tiny dent, maybe just a scratch.
Yeah.
Looks totally fine.
Exactly. Visually, it looks harmless.
Yeah.
But we're going to explore how that barely visible damage can secretly reduce the lifespan of advanced aerospace materials by a staggering 93%.
It really is the ultimate deceptive failure. I mean, we're dealing with this structural compromise that is basically invisible to the naked eye, but catastrophic under the surface.
Right, and Lobanov's team focused specifically on GFRPs, so glass fiber reinforced polymers. We know these composites are super strong and lightweight, which is why aviation uses them constantly. But they face a lot of operational damage out in the real world.
Oh, for sure. You have bird strikes or flying runway gravel, even luggage carts bumping into a parked plane.
Yeah, and to test this, the researchers took perfectly good strips of GFRP and just intentionally damaged them. They used a steel blade for a 10 mm scratch and a steel sphere to press dents in at massive forces. We're talking 10, 12, and 15 kilonewtons.
And for context here, 22 kilonewtons completely shattered the material in their preliminary tests. So hitting it with 15 kilonewtons is really pushing the absolute boundary of the composite's integrity.
Right, they're really battering these things. But when they pulled the damaged strips apart to test their initial strength, the readouts are honestly kind of wild. The dents and scratches didn't change the material's stiffness at all.
Exactly. So to a casual observer holding that damaged part, it feels exactly as rigid as a brand new one.
But that deceptive stiffness is the whole danger. Because despite feeling perfectly stiff, the ultimate breaking point was severely compromised. When they tested the 15 kilonewton dent, they found the maximum breaking stress actually dropped by 30%.
The structural integrity is broken down, but that weakness is totally masked by the fact that the stiffness hasn't changed.
And a 30% drop in breaking stress is bad enough. But planes don't just experience one giant pull, they endure fatigue loading. Thousands of cycles of stress over years of flights.
Which is where the cyclic data comes in and exposes the true vulnerability. Under that repetitive cyclic loading, the sample with the 15 kilonewton dent saw its fatigue life plummet by 93% compared to an undamaged sample.
93%.
Yeah.
The lifespan of the part just evaporates. And looking at how it actually breaks on a microscopic level is really striking too.
It is. The surface scratch causes the layers to peel apart, which is delamination. But those massive dents actively cause the internal glass fibers to snap.
So the crack initiates right at the surface of the dent and then just grows underneath the intact outer polymer layers.
Exactly. Meaning a standard visual inspection is going to miss the fatal flaw completely until the part fails outright.
So the next time you're on a flight, you can definitely appreciate why engineers are so obsessed with detecting this barely visible impact damage. A material can look perfectly fine and feel completely stiff, while secretly harboring a fatal flaw.
It leaves you with a fascinating question to ponder. If our most advanced lightweight composites can be structurally devastated by a single dropped wrench, how might engineers in the future design materials that can automatically detect or even self-heal these invisible microcracks before they lead to failure?
That is definitely something for you to mull over the next time you're cruising at 30,000 feet. Thanks for joining us for this deep dive.